Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about thermodynamics, especially as they apply to organic chemistry. The structures on the upper right show the homolysis of ethane into two methyl fragments. This type of homolysis represents the breaking of a carbon-carbon bond, and is the type of reaction studied in determining bond dissociation energies, which we'll talk about in a little bit. In general chemistry, you probably learned about the first law of thermodynamics, the so-called law of conservation of energy, that energy cannot be created or destroyed except in certain kinds of nuclear reactions. In general chemistry, you probably applied the law of conservation of energy in helping to understand that the energy change that occurs during a reaction is the sum of the work done and the heat transferred, and so if you knew one of those things, you could calculate the other. Or if you had some way of determining that the work done was negligible, then you could use heat in equals heat out. In organic chemistry, we're a little bit more concerned about the second law of thermodynamics, that the entropy of the universe must increase for any spontaneous processes. And we can represent this law as following. Delta S, where S is the letter most commonly used for entropy, of the universe must be greater than or equal to 0 for spontaneous processes. Generally, entropy of the universe is increasing. The universe is divided into two parts, the system and the surroundings. And so when we are talking about the entropy of the universe increasing, that does not mean that the entropy of the system has to increase. The entropy of the system can decrease as long as this entropy of the surroundings is increasing to compensate. In chemistry, we usually define the system to be the reaction. Those molecules which are undergoing the chemical change are the system. Everything else, the solution they're in, the glassware that's holding that solution, the stir plate that beaker is sitting on, the lab, the chemist, everything else is the surroundings. It turns out that the entropy change of the surroundings is proportional to the heat transferred from the system to the surroundings. In our expression for the entropy of the universe, we can replace delta S of the surroundings with the delta H, or the enthalpy change of the system, divided by the temperature. And there's a minus sign in front of that to indicate that heat is being transferred from the system to the surroundings. And remember again from general chemistry that H, enthalpy, is equivalent to heat under constant pressure situations. And if you want to know more about where enthalpy comes from, I'll go back and review enthalpy. Okay. So we now have a new equation. Delta S of the universe equals delta S of the system minus delta H of the system divided by temperature. The goal is to try to equate everything to the system because we can measure the system. It's hard to measure the surroundings, which include the room that you're in, stuff going on in Cleveland, Mars, the Andromeda Galaxy. It's really difficult to measure the entirety of the surroundings. So it's really easy to frame the change in surroundings as a change in the system. If we multiply through this equation by minus 1 over t, we can get a slightly different equation. So now we have minus T delta S of the universe equals minus T delta S of the system plus delta H of the system. And it turns out that T delta S of the universe is the definition of something else we've worked with in general chemistry before. Delta G, the free energy of the system. So now we have framed the entire entropy change of the universe in terms of the system. So now we have an equation entirely in terms of the system. The free energy change of the system is equal to the enthalpy change of the system minus the temperature times the entropy change of the system. And as a reminder from general chemistry, free energy is equal to the maximum capacity to do non-mechanical work, which we'll interpret as chemical work, the forming and breaking of chemical bonds. We can estimate the free energy change of the system if we can estimate the enthalpy change and the entropy change of the system at a given temperature. One way to estimate the enthalpy change of a reaction is to use the heat of formation method. You probably use this in general chemistry to estimate the enthalpy change of various reactions. This method takes the sum of the heats of formation of the products and subtracts the sum of the heats of formation of the reactions. It's an application of Hess's law. So if we have this reaction of 2-bromopropane plus water forming 2-propanol and hydrogen bromide, we can use heat of formation data to estimate the enthalpy change of this reaction. This method is dependent upon having access to heat of formation data for all of the substances in your reaction. Here are the heats of formation for the 4 substances in this reaction. The heat of formation of 2-bromopropane is minus 129.1 kilojoules per mole, water is minus 285.8 kilojoules per mole, 2-propanol is minus 318.2 kilojoules per mole, and hydrogen bromide is minus 36.3 kilojoules per mole. And all we have to do is take the sum of the enthalpy changes of the products and subtract the sum of the enthalpy changes of the reactants, which I've done here. So the sum of the enthalpy changes of the product is minus 354.5 kilojoules per mole, and the sum of the enthalpy change of the reactants is minus 414 kilojoules per mole. And when you work it out, this is an enthalpy change of plus 60.4 kilojoules per mole. So this is a reaction that is slightly endothermic. The reactants have, or some amount of heat needs to be added to the system in order for this reaction to occur. We don't always have access to enthalpies of formation, and so sometimes we might want to use another method. In organic chemistry, we often can find bond dissociation energies. These are the energies required to break covalent bonds into their constituent atoms or pieces. For example, the bond dissociation energy for hydrogen, H2, is 435 kilojoules per mole. It takes 435 kilojoules of energy to break 1 mole of hydrogen molecules into 2 moles of hydrogen atoms. The bond dissociation energy for the carbon-carbon bond in ethane is 368 kilojoules per mole. It takes 368 kilojoules of energy to break the carbon-carbon bonds in 1 mole of ethane to make 2 moles of methyls, which they're not methyl cations or anions, these are methyl radicals. Bond dissociation energies are always positive because it takes energy in to break chemical bonds. So the bond, and as I was just saying, the bond dissociation energy is the energy required to break a covalent bond homolytically, which means one electron in that bond goes with one atom or group, the other electron goes with the other atom or group. So now if we go back to our sample reaction, with some bond dissociation energies, we can estimate the change in energy of the reaction. In this particular case, using the bond dissociation energy method, we do the sum of the bond dissociation energies of the reactants, because that's where we put energy in, minus the sum of the bond dissociation energy of the products, because forming bonds releases energy. There are 2 chemical bonds broken, the bond between the carbon and the bromine in 2-bromopropane, and the bond between hydrogen and oxygen in water. And their bond dissociation energies are listed there, the 285 and 498, and they add to 783. 2 bonds are being formed, an oxygen-carbon bond in 2-propanol and a hydrogen-bromine bond in hydrogen bromine, and they add up to 763 kilojoules per mole. The difference between those is 16 kilojoules per mole, and so we don't get quite the same answer as we do for the heat of formation, because bond dissociation energies are not always for the representative compounds that are in our specific reaction. They might also not be in the specific state of the substances, where heats of formation are for defined states, liquid, gas, etc. But in this particular case, we at least got the correct sign, positive. This is a slightly endothermic reaction. Estimating entropy change is a little bit more challenging. The entropy is proportional to the number of degenerate states in a system, and by degenerate states I don't mean that we have states in which the molecules are misbehaving, but instead a degenerate state in thermodynamics are arrangement of the things in that system that would have equivalent energy. So we can say entropy is proportional to the number of ways we can arrange the molecules in a system so that the system has the same energy, and we can't otherwise tell the difference between what's going on. Turns out this is really, really hard to calculate. And so we're not going to spend any time here trying to estimate specific entropy values. We're just going to try to estimate the sign of or the direction of entropy change. We can estimate the change in entropy in a couple of ways. Mostly what we're looking for are ways in which the number of possible states increases, and they increase when solids are converted into liquids. Liquids have more kinetic energy and more different possible arrangements with the same kinetic energy. Likewise, the number of states increases when liquids are converted into gases for the same reason. When the number of particles, molecules, atoms, etc. increase, you also get an increase in entropy. More particles means more different ways you can arrange those particles. You also get an increase in entropy when the conformational freedom of a molecule increases. So when a cyclic molecule becomes acyclic, cyclic molecules have fewer conformations available. When ring size increases, larger rings are more flexible than smaller rings. And when multiple bonds become single bonds are rigid, single bonds can rotate. The reverse of all of these things cause a decrease in entropy. So the number of degenerate states decreases when gases are converted to liquids, liquids are converted to solids, the number of particles in a system decreases, acyclic molecules become rings, ring size decreases, and single bonds become double or triple bonds. Here's an example where we can estimate the entropy of a particular reaction. And to help us out, I've given the chemical states of the substances in the reaction. If you don't have access to state information, then you need to base your judgment on other factors based on the structures of the molecules. So for this particular system, we have a reaction where two molecules are converted into one molecule. This would be a decrease in energy, decrease in number of particles. We have acyclic molecules being converted into a cyclic molecule, also decrease in entropy. We do have a loss in the number of double bonds, which probably would be a slight increase in entropy, but it'd be difficult to say based on where these things ended up. Also, we have two reactants that are gases and the product is a liquid. This is a decrease in entropy. Overall, the entropy of this system decreases. Let's do another example with a similar set of molecules, but this time we have two reactants and two products. And again, I've written out the equation showing the states that all of these substances are in. In this case, we have two molecules on the reactant side and two molecules on the product side. So we would estimate that there's not a big change in the entropy. I'm saying delta S is approximately 0 here because delta S is probably not perfectly 0, but we don't have enough information to know whether it's a positive change or a negative change. We're going from one ring and one acyclic molecule on the reactant side to one ring and one acyclic molecule on the product side. Probably not a big change there. On the reactant side, we have one liquid and one gas. On the product side, we have one liquid and one gas. Not a big change in entropy for that criterion either. The only difference that we have from the left to the right is that we have one 5-membered ring on the left, and the ring on the right is a 6-membered ring. Because we have an increase in ring size, we might be able to say that entropy is increasing here. Overall, entropy is probably increasing, but because we have three situations that are not changing the entropy greatly, but we don't know whether they're positive or negative, it's hard to say for certain that entropy is probably increasing, but entropy is probably increasing. Up next, we're going to do some practice problems in thermodynamics. Thank you for watching.